April 1940, Inglewood, California. The British Purchasing Commission delegation sat across the conference table from North American aviation executives with an urgent request that would reshape aerial warfare. Britain needed fighters desperately, immediately. The Battle of Britain loomed, and the Royal Air Force faced a fighter shortage that threatened the nation's survival. The Commission wanted North American aviation to build Curtiss P-40 Warhawks under license, cranking out proven fighters as quickly as American production lines could deliver them. What happened next in that meeting would set in motion one of history's most improbable aircraft transformations, but the path from that April conference room to dominance over Berlin would require 4 years, a forbidden engine swap, and one engineer's willingness to defy military procurement orthodoxy. The man who would change everything was Edgar Schmude, born in Germany in 1899, who had seen his first airplane at age 8 and never recovered from the experience. Largely self-taught in aeronautical engineering through obsessive study rather than formal university training, Schmude had immigrated to America carrying dreams of building the perfect fighter aircraft. By 1940, he led North American aviation's design team, known among colleagues for meticulous attention to aerodynamic efficiency and stubborn insistence on innovation over convention. When company president Dutch Kindleberger proposed simply building P-40s as the British requested, Schmude pushed back with characteristic bluntness. "Well, Dutch, don't let us build an obsolete airplane, let's build a new one." The decision to design a completely new fighter rather than manufacture an existing model was either brilliant or reckless, but what made it extraordinary was the timeline. The British needed aircraft immediately. Designing a fighter from scratch typically required years. Schmude promised to deliver a prototype in 120 days. What emerged in those frantic months was revolutionary in its attention to aerodynamic refinement. Schmude obsessed over every surface, every rivet, every potential source of drag. The Mustang featured a laminar flow wing that maintained smooth airflow over the wing surface far longer than conventional airfoils, reducing drag dramatically. The fuselage was streamlined with obsessive attention. The radiator scoop incorporated a Meredith effect that actually converted cooling drag into forward thrust. Every detail reflected Schmude's European engineering background merged with American manufacturing pragmatism. The prototype rolled out on September 9, 1940, exactly 102 days after the British contract was signed. Test pilots praised its handling characteristics, its stability, its responsiveness. The British placed orders. The US Army Air Forces began paying attention. Everything looked promising except for one catastrophic flaw that would nearly doom the entire program. The Allison V1710 engine installed in early P-51 models performed adequately at low to medium altitudes, providing reasonable speed and good handling for ground attack and reconnaissance missions. But above 15,000 feet, the Allison-powered Mustang suffocated. The engine lacked an efficient supercharger for high-altitude operation, meaning that as the aircraft climbed into the thin air, where the air war over Europe was actually being fought, power output dropped precipitously. For bomber escort missions over Germany, where B-17 Flying Fortresses and B-24 Liberators flew at 25,000 feet or higher, the early Mustang was essentially useless. U.S. Army Air Forces commanders already committed to the Republic P-47 Thunderbolt and Lockheed P-38. Lightning, both designed for high-altitude combat, saw little reason to adopt another fighter that couldn't fight where the real war was happening. The Mustang was relegated to low-level tactical reconnaissance with the RAF, respected for its handling and range, but dismissed as a frontline fighter. By early 1942, the aircraft that had generated such enthusiasm seemed destined to become a footnote, an interesting design that fell short when it mattered most. But across the Atlantic, Royal Air Force test pilots and engineers saw something American evaluators had missed. The question wasn't whether the Mustang was good enough as designed. The question was whether that magnificent airframe could be transformed by changing its heart. In April 1942, Ronald Harker, a Rolls-Royce test pilot and engineer, flew an Allison-powered Mustang at Farnborough. His report would prove more consequential than most combat action reports. Harker wrote that the Mustang airframe was possibly the finest he had ever flown, superior in aerodynamic efficiency to anything currently in production. The handling was exceptional, the range impressive, the potential obvious. The only significant flaw was the power plant. Harker's radical proposal was to install a Rolls-Royce Merlin engine, the supercharged marvel that had powered Spitfires through the Battle of Britain, into the American airframe. The Merlin featured a two-stage supercharger that maintained power output at high altitudes. Harker believed that marrying the Merlin's high-altitude performance to the Mustang's exceptional aerodynamics would create something unprecedented. The proposal faced immediate resistance. To American military procurement officers, installing a British engine in an American fighter violated both practical logistics and national pride. The US was spending enormous resources developing domestic aircraft and engines. Adopting foreign power plants would create supply chain complications, require retooling production facilities, and implicitly admit that American engines were inferior. Beyond practical objections lay deeper concerns about dependence on foreign technology. The resistance was not entirely irrational. Military logistics demanded standardization and simplicity. Introducing a British engine meant different spare parts, different maintenance procedures, different training requirements. For supply officers managing a global war effort, such complications were legitimate concerns, but the British didn't wait for American bureaucracy to reach consensus. In late 1942, Rolls-Royce engineers in England began the conversion work. The engineering challenges were substantial. The Merlin was heavier than the Allison, requiring modifications to engine mounts and adjustments to maintain proper weight distribution. The cooling system needed complete redesign. Air intake geometry required careful reshaping to feed the supercharger efficiently. Each problem required solutions that maintained the Mustang's aerodynamic excellence while integrating a fundamentally different power plant. The first Merlin-powered Mustang flew on October 13, 1942. Test pilot Ronald Shepard climbed into the modified aircraft with appropriate skepticism. When he pushed the throttle forward and the Merlin's supercharger spooled up, delivering power the Allison had never managed at altitude, his reaction was immediate. "This thing is unbelievable. It is a completely different airplane." The test data confirmed what Shepard felt instinctively. Top speed increased to approximately 440 miles per hour at 30,000 feet, a dramatic improvement. Climb rate doubled, service ceiling increased substantially. Range extended past 1,600 miles with external drop tanks. The Merlin Mustang wasn't just better than the original, it was better than virtually every other fighter in the sky. Back in California, Edgar Schmude received the British test data with vindication and frustration in equal measure. Vindication because the results proved his airframe design was as good as he believed. Frustration because American resistance meant his aircraft was still relegated to secondary roles while the solution was obvious. Schmude began working closely with both Rolls-Royce engineers in Britain and Packard Motor Company in the United States, which held the license to manufacture Merlin engines domestically. The collaboration was unofficial, irregular, and exactly what the situation required. Schmude's team addressed the technical challenges methodically. Weight distribution calculations ensured the heavier Merlin wouldn't compromise the Mustang's flight characteristics. Cooling system redesigns incorporated improved radiator designs and optimized airflow. Engine mount modifications transferred the Merlin's power loads safely to the airframe structure. Every modification maintained Schmood's original emphasis on aerodynamic cleanliness and structural efficiency. By early 1943, North American aviation had produced American-built prototypes designated XP-51B, incorporating Packard-built Merlin engines. The first XP-51B flew in November 1942, and subsequent test flights confirmed that American production could replicate the British conversion's performance gains. Air Force observers who had dismissed the Allison Mustang watched the XP-51B demonstrations with growing interest. The performance was undeniable. The aircraft outperformed every American fighter currently in production across almost every metric. General Henry Hap Arnold, commanding general of the U.S. Army Air Forces, recognized that the bomber offensive over Germany was failing due to unsustainable losses. B-17 and B-24 bombers flying unescorted deep penetration missions were being slaughtered by Luftwaffe fighters. The P-47 Thunderbolts and P-38 Lightnings provided excellent protection within their range limits, but they couldn't escort bombers all the way to Berlin and back. The Mustang could. Schmood personally advocated for rapid adoption of the Merlin Mustang, presenting data to skeptical generals who had invested heavily in existing fighter programs. His reputation for engineering excellence carried weight, and the test data was irrefutable. His colleagues knew him for one particular saying, delivered with characteristic bluntness. Any damned fool can criticize, but it takes a genius to design it in the first place. By spring 1943, orders were placed for large-scale production of the P-51B and subsequent improved models. The institutional resistance hadn't disappeared entirely, but momentum had shifted decisively. The aircraft that nobody wanted 2 years earlier was about to become the weapon that would break the Luftwaffe's back. Schmood's genius wasn't just in designing an aerodynamically superior airframe, it was in recognizing that perfection required adaptability. He had created a platform capable of accepting improvements, and when the British showed him what was possible with the right engine, he fought bureaucratic resistance to make it happen. The Merlin-powered Mustang entered combat with the Royal Air Force in late 1943, designated Mustang Mark III in British service. The results were immediate and dramatic, but the real transformation came when the US 8th Air Force, conducting the daylight strategic bombing campaign against Germany, adopted the P-51B and later the refined P-51D as their primary long-range escort fighter in spring 1944. The impact on bomber operations was revolutionary. Missions that had previously resulted in devastating losses, sometimes 10% or more of the attacking force, suddenly became sustainable. B-17 and B-24 formations that had fought their way to targets in Germany without fighter protection now had Mustangs flying protective cover from takeoff in England to the target and back. Luftwaffe pilots, many of them veterans with years of combat experience, found themselves facing an aircraft that matched or exceeded their best fighters in almost every performance category. The Focke-Wulf Fu-190 had dominated Allied fighters through much of 1942 and 1943. The Messerschmitt Bf-109G remained formidable, but the Mustang was faster than both at altitude, could outturn the FW-190, and had range that allowed it to fight over Berlin and still return to England. By summer 1944, the air war over Europe had fundamentally changed. 8th Air Force missions that had been desperately costly in 1943 became routine in 1944. Bomber loss rates dropped from unsustainable levels to manageable attrition. Luftwaffe losses mounted as German fighters were forced to engage American escorts or allow bombers to reach targets unopposed. The Mustang gave American commanders operational flexibility that hadn't existed previously. Deep penetration raids to Berlin, synthetic fuel plants, and aircraft factories could now be planned with reasonable expectation that most bombers would return. The strategic bombing campaign that had nearly failed due to unsustainable casualties was revitalized by one aircraft. Every bomber that returned safely represented 10 crew members who survived to fly again. Every mission that achieved its objective without catastrophic losses meant industrial targets were destroyed and the German war economy was degraded. The cumulative effect over hundreds of missions was the destruction of the Luftwaffe's ability to defend German airspace. By early 1945, American bombers flew over Germany with relative impunity because American fighters, primarily Mustangs, had achieved air superiority so complete that effective defense was impossible. Edgar Schmude never sought fame for his achievement. While generals planned campaigns and pilots earned ace status, Schmude returned to his drafting table and continued designing aircraft. His post-war career included leading the design team for the North American F-86 Sabre, the swept-wing jet fighter that would dominate the skies over Korea. He moved to Northrop Corporation in 1952, serving as chief engineer and contributing to designs including the F-5 Freedom Fighter and T-38 Talon trainer. His career spanned the transition from piston engine fighters to supersonic jets, and his influence on American fighter design extended across decades. But the P-51 Mustang remained his masterpiece, not just for its technical excellence, but for what it represented about innovation under pressure. The broader lesson of the Mustang's transformation extends beyond technical achievement to questions of institutional flexibility and willingness to adopt better solutions regardless of their origin. American military culture in 1942 and 1943 naturally resisted installing British engines in American fighters. The resistance was understandable given logistics concerns and national pride, but it was also nearly catastrophic. If British engineers hadn't conducted unauthorized testing, if Schmude hadn't fought for American adoption, if generals hadn't eventually recognized that performance mattered more than politics, the bomber offensive might have failed. The Mustang succeeded because talented people recognized a problem, identified a solution, and persisted until institutional resistance gave way to demonstrated capability. The P-51 Mustang flew in combat until the end of World War II and continued in service with various air forces for years afterward. Its distinctive profile became an iconic symbol of American air power. Pilots who flew the Mustang remembered it with particular affection. The aircraft was fast, maneuverable, reliable, and possessed enough range to go anywhere and come home. In an era when single-engine fighters rarely exceeded 500-mile combat radius, the Mustang could fly 1,600 miles with drop tanks, fight for 15 minutes over the target, and return with fuel reserves. That capability, combined with performance that matched or exceeded any opponent, made it the most complete fighter aircraft of the war. The transformation from rejected mediocrity to legendary dominance required 4 years, multiple countries' contributions, one engineer's stubborn insistence on excellence, and institutional flexibility to accept that the best solution wasn't always the expected one. That the best American fighter of World War II flew with a British engine is a historical irony that Schmude would have appreciated. He understood that excellence required pragmatism, that the perfect could indeed improve upon the good, and that sometimes the most patriotic choice was accepting help from allies who offered the key to unlocking potential that had been there all along.